Hello, and welcome back to Learning with Lee. In today's episode, we are going to continue to take a look at dynamic memory allocation, pointers, and the merge sort algorithm. In particular, we are going to be comparing our earlier merge sort algorithm that happened to use malloc every time this merge function was called, which resulted in us having to allocate memory multiple times and then free memory multiple times. In particular, we're going to be comparing that to a version which I had asked you to create on your own as a bit of an assignment between the last episode and this one. A version in which it only uses malloc once, in the very beginning, so as that we don't have to do these calls to malloc and free more than a single time. Before I get too far into the code, let me take a look at how this changes our general algorithm here. And the general change now is that originally we only had this one array, and then, as needed, we would create a temp array over here, and then we would destroy it once we were done with it. What we're doing now, though, is we're creating two arrays of the same size. And the major trick with it is that what I can do is I can say, okay, this one here has some set of numbers in it. And what I can then do is I can go, okay, I'm going to merge like these two over, these two down, these guys over, and this guy down. And what it will then end up having is it'll have effectively these local sorted subarrays. And what I can then do is I can then basically merge back from this bottom array into this array up here. And I can do this at each effective layer of the algorithm. So if we consider basically how we have all these splits here, or down here, for example, these, this initial merging step would be layer 0. Then down here we'd have layer 1, and so on and so forth until we have finished up the merge. And all we have to really do at each of these layers, because we're going to be effectively swapping which one we merge into, is swap around the two arrays. However, there is one other minor problem, and that is that initially only this array up here has any data in it. So if we take a look at the code, one of the things you'll notice is I'd use this mem copy here. Now, I could be a bit more discerning with how I'm using that and take a look at whether or not we're going to have an even or odd number of layers. Because so long as we're starting out copying from this top array into the bottom array first, it doesn't matter that the bottom array doesn't have anything because it will get fully populated by the time we move on to the second layer. However, it just is a bit more simplistic to go with, we're just going to do a mem copy no matter what. We're going to guarantee that both of them are populated with the exact same data, and then we'll go from there. So it's a bit of a simplification. It can impact your performance slightly, but as you'll see at the end of this, even with that minor performance hit, it still is far, far more efficient than the other earlier version I had shown you of merge sort. And that is because malloc, calloc, alloc, as well as to a certain extent free, all end up actually being fairly expensive operations. So what we happen to then do is okay, we have our array, as you could guess, so as we now have a second array off of our first one. We're going to be passing in both of those pointers, both of those arrays. Both of them have the same size, so we only need to use the same start index and end index. We don't need to create a second copy of those for the second array. Then in here, same thing as before. Once we're down to a single element, we can stop recursing and go back up to the previous one to do the merge. Split index, exact same step here. So the next thing you're going to see is this right here, this recursive call. And the major thing that's important to note is that in here I've named these to and from. And the important thing is that in the final version, we want our sorted array going into the original array, which is why I called it so as that this to, whatever we're copying or sorting into, happens to be the original array that we had, and we're passing from the other one. So what we then do in here happens to be, we want to, at the layer below that, we want to ensure that, just to sort of go over it from our example over in here, let's say that I'm looking at this guy here. I have my final merge layer, let's just put it down here, for example. And this one here needs to go into ARR. Well, at this stage here, we need to then have effectively the two halves of ARR sorted independently within our temporary array. So I'm just going to call that T for now for simplicity's sake. So we need to go basically from ARR at this level into T so that we can then go back into ARR at the final layer. Alternatively, and this would be a more expensive thing I could do, is I could basically at each layer end up sorting into T, basically go from ARR into T, and then copy that information back into A once the sort is done, so as I don't overwrite anything mid-sort. And while that could be done, that effectively doubles the amount of work we have to do in terms of storing the information, and that's another spot in which we can save on performance and make this much more efficient. And by just swapping these arrays around at each layer, so as that once again, we have at one layer here, at layer 0, we would have effectively A, though technically we might actually start from T at that layer, because really it's going in the opposite direction. So down here, we want A, up here we want T, then we want A, then up here we want T, and so forth, so on and so forth, until we ended up recurring all the way down to the bottom. And that happens to be why we do this here. Otherwise, it's the exact same as before. And then on the merge, because of the fact that we want to sort into a specific one, we had to slightly then modify the merge so as we go from one of them that's basically at the layer up sorted, then down to this one here, which is the more sorted version stored in there. I've cleaned up the merge algorithm slightly since our previous one, as well as this has allowed us to make this a bit simpler anyways. Because of the fact that we don't need to have a new custom array for every one of these, we don't have to start 0. We can just start at the start index in our second array. So since wherever we are in our first array effectively is getting copied into the same memory in our second array, so basically if we're dealing with these elements over here, they're just going to end up using these same memory spots. They might be reordered, but they're going to use the exact same memory. Same thing for if I'm using just like these two spots in here, they're going to use the same two down there, and so on and so forth. So it's a matter of, I can use the exact same indices for one as the other. So the same start index, the same end index. So that means I no longer have to care about the count of the items. It means I no longer have to care about some of the other stuff I had to worry about before when I was dealing with I, in order to make it its own custom thing. I didn't have to start it at 0. So this one just starts at the end index, ends at the end index, and goes through. And otherwise, this section here is the exact same, other than the fact that we don't have the little prep stuff of creating the temporary array and then freeing it at the bottom. And then to take a look at the actual performance benefits we gain out of the difference here, I can build this and run it, and it'll take a little bit, and the longest thing here is actually the printing of the lines here, and that's part of the reason why you can see that graphical glitch where initially there was a line up here which was for the original sorting algorithm, and there's this line down here for the alternative, but unfortunately because of the way Eclipse works, as well as because of the timing in these couts, because there's so much data being output right now, because in order to make this actually a noticeable difference, I gave this a size of 100,000. Unfortunately, much more than that, even if I take out both of these sorting algorithms, the memory usage alone causes Windows to think that the program has crashed. So, this is about as large as I can get it without Windows saying, your program isn't responding, we need to terminate it. Just due to things such as the allocation of the arrays and the memcopy portion of it alone. So, what you'll see is that right here, it took about half the time of the other algorithm. And really the only major changes that we ended up doing to it was the fact that we're only using malloc once, we're only using memcopy once, and we're only using free once. Otherwise, there isn't that much of a difference between this one here, as well as then this version of it over here. So, I hope that that gives you a decent idea of why malloc, memcopy, and free are things that when you use them, you have to be very careful with them. Aside from the fact that you have to be careful about making certain to free anything that you end up allocating, which itself is another whole bag of worms that we're going to probably get into in the next episode. What you then have to do here is you have to consider the fact that there is a fair amount of memory overhead in using the heap as opposed to using the stack. So, what I would ask you to do for today's episode, and I'm going to make this one a bit short given how long and at length I spoke in the previous episode, I would recommend going over this, comparing the advantages of however you had implemented it previously to mine, messing around with it, seeing different ways in which you can implement this, seeing different ways in which you might be able to make it a bit cleaner or a bit more efficient. Possibly getting it so as it only does the memcopy if it absolutely has to do the memcopy. But in general, messing around with it, seeing what you can do with it. And thank you very much for watching. I hope you've had a wonderful day.